talk. So let's welcome Dr. Goh.
Thank you. You mentioned about Jim Clark. It reminds me, about 22 years ago, I used to work for him. Yes, at SGI. He was a great guy. So please remind me where the boat is. I'd like to have a look. Yeah.
Right
later. Yes. Thank you. Thank you all for coming. In fact, Jim Brinker, you were at SGI when Jim Clark was there? Not yet, huh? Way back. Huh? Oh, Dale Sutton. Yes, was that there? Way back, yes. So today, we are at a HPC conference, but I would like to spend a bit more time on big data, which is the result of HPC. Let's have a look at HPC sites that we have. I know that we are going public on YouTube, so I had to blank off everything on the right of that screen. But in the interest of our customers, this is the list of HPC sites. The top 3 are petascale systems. Some of the names are blanked off, especially those in blue, because the blue ones are new systems we have yet to either install or have accepted. So the customers are not ready to have their names published. But you can see that we are talking of the order of 100,000 cores, of the order of 1 or 2 petaflops type system. But if you look at the larger system we have, which is a 200 cabinet, 200 rack NASA machine, correspondingly, it has 40 petabytes of data. So this corresponding list shows these HPC customers. Not all of them are on this list, but many of them are. The amount of data that they generate due to their HPC systems that is being managed by SGI. So NASA, having the largest HPC system, also has the largest storage system from us, in this case 40 petabytes in size. You will also see NOAA GFDL, our HPC customer there, at 30 petabytes. And these sites are growing very fast. You will also notice that some of these on this list, having big data, are not HPC people, like the NBA. Over here, recording basketball games, and in Weta, all the Lord of the Rings videos are on this site at 10 petabytes today. So every time they create a new Lord of the Rings movie, they would use some old frames from previous movies, and this is their data repository. You will also notice a few that are instrument-based. Right, Sarah, which is storing data from the Large Hadron Collider, Cicero, who is starting to set up for the Square Kilometre Array, and so on. Let's have a look at them. The instrument people, other than HPC, that are generating big data. This is ITER, the International Thermonuclear Experimental Reactor. They're trying to build a fusion reactor for energy generation. So much of these experiments, the data is going into our data repository. Right? The whole goal here is to try and sustain a fusion reaction long enough, and of course with net gain. Put in less power than you get out. Okay, so that's in addition to HPC, I like also to mention that big instruments also generate massive data. The second example is the Large Hadron Collider in between Switzerland and France. This is a big pipe that rings between Switzerland and France border, and generating lots of data. Many repositories. This one that we are managing is in the Netherlands. They're talking orders of exabytes in a day or two. The next one that is of high interest being worked on right now is in Australia. SKA stands for the Square Kilometre Array. The idea is to put 2,000 to 3,000 radio telescope in an array. These are 15-meter dishes, but 2,000, 3,000 of them in an array. And it is projected that this thing is going to generate about an exabyte a day. I don't know how we're going to store that thing, but we'll fill up our entire repository in a few seconds. The whole NASA repository will be filled in a few seconds. So I think there will be lots of data reduction. For example, if you are bringing in data raw at a petabyte a day, it works out to be roughly a exabyte a day. If you're taking in raw data at about exabyte a day, it works out roughly to be about a petabyte a minute. Every minute you are taking in a petabyte. So you have to do some data organization before you store. So hopefully 100x reduction. That works out to be a petabyte an hour. Yeah, a bit more manageable. A petabyte an hour. That's about probably about 1 terabyte a second. And after organizing, perhaps analytics you reduce by about 100x. That's about petabyte a day. And finally, visualization. And for some customers, all that exabyte at the front end is reduced to a single bit, whether go or no go, right? So just wanted to show this slide to let you know that many of these sites don't store everything raw. They go through some data reduction process. But all in all, the point I'm trying to make here is that regardless of whether you are HPC or you are big instruments, we have a huge problem. We are talking about coming up to orders of exabyte a day type instruments or exascale machines that are generating these types of data. We have to figure out a way to deal with them. So this is what I'm going to spend some time on today, how to deal with HPC data and or how to deal with big instruments data. Well, can we afford to store all that data in fast hard disk and solid state disk? It gets very tough. If you're talking about an exabyte repository, it will cost you today to build an exabyte repository of say SSD. It'll probably cost you as much as your exascale machine. So you have to find some way of storing things cheaper onto tape, or what is emerging is onto 0-watt sleeping disk, not the 1 or 2 watt sleeping disk, but full shut-down. Shut-off disk, 0-watt sleeping disk. But the next problem is that if you put everything on the 0-watt sleeping disk, you get a performance problem because when you need the data, you have to spin up the disk. Worse still, if it was on tape, you have to go and retrieve the tape. So you want to use a system that is there's a mix of both, where the high-performance one on the left or in front, right, is somewhat like your cache. And then the big repository at the back is your main store. Therefore, you need a piece of software that does the promotion and demotion between your front fast storage and your back-end slower storage. And that's where HSM come in. It is my belief that HSM and 0-watt sleeping disk will become more and more important as we move forward, because we just can't afford to store 10 exabytes of data on spinning disk. Even if you can afford it, you wouldn't want to waste the energy of spinning a million disk drives, right? If you are only going to read 0.1% of them at any one time, right? To have a million disk drives all spinning. If you think a million disk drives is a lot, we have Amazon that is spinning about 250,000 disk drives right now, right? The Amazon EC2 and S3 cloud storage system. Yeah. So a DMF system, a HSM system, Hierarchical Storage Management System, to which we have one called DMF, is what we use to do this transparent promotion and demotion of your files between fast and between fast and cheap storage. How do we do it? I'm going to show you an example. If a user lists this fast and this storage files, you should never know whether your files are kept here or kept there to the user. The user should not care, right? It's left to the HSM system to decide where to put the files based on how recently they have been used. Let's now have a look at what the user sees in their files. You see, there are 4 files in my directory, and the user doesn't know where all the files are, except if the administrator does this, issues the administrator command. Then it tells you in an extra column that a regular file, REG, are on your fast storage. OFL means it is being put quietly into the 0-watt sleeping disk. Because why? That file called seldom.dat has not been touched for a while. So the system decided, based on your policy that you can set of how long it has not been touched, has moved it to the back. Now, what happens now if the user now say, show me this file called seldom.dat? If I hit the return, it will take a while for that file to come. That's the penalty. Because now it's going there to spin up that disk, that has been 0-watt sleeping, right, up to a stable enough speed, and then the file comes. So that's your penalty for paying less energy to, because the drives are spun down, right? For paying less because those drives are much cheaper. They are not as high performance. And in return, you have to give it that 15-second wait before the file comes. Yeah. Let's now monitor all these files, right? I'm just going to open up another window. And the top window monitors what's going on in that column. You just notice what's going on in this column. And I'm going to issue some commands to say, give me all your files. Yeah. It's going to list all the files. And then now, based on some policy, I've decided that the policy has decided to move all those files to the 0-watt sleeping disk. I'm going to force the command. And let's see what happens here. Star.star. Force everything to the 0-watt drives. Right? I hit the return. So based on some policy, those 4 files have not been touched for about a week. Your policy says move them to the cheap drives. Hit return. You can see it's all going offline. Yeah, one at a time. The top one is migrating. So basically, it's spinning up these drives that has been sleeping. And then to move, migrating means is in the process of spinning them up and then moving this file. So there you go. All the files are now offline. And guess what? The only thing the user will tell whether the files have moved offline, if they don't have this column, is that when they look at the total, the amount of this storage is used on a cheap drive, on the expensive fast drive, is 0. You notice? Although your files are still available, the amount of space is using up on your fast drives is 0. Yeah? And then if you say ask for all the files again, to bring them all back, you can see they are all coming back. Yeah? So, and you don't have that 15-second wait because it so happened that the drives are still spinning. They have not been shut down yet. Yeah? So this is what we believe will become almost standard for these large data repository, because it's just wasteful to keep, say, 250,000 or 100,000 disk drives all spinning at high speed, let alone you being able to afford all these to be SSDs. But you just use your fast drives and expensive all spinning drives as your cache, while your majority of your files are there. The other advantage is that every time you have new budget, you can decide whether to spend that budget on performance or you can spend that budget on capacity. You just increased the portion that you feel is more important to you. So this is the picture. This is one method where you have your HPC systems. It generates data, and all that data is then put on this one big storage system. The file system could be Lustre. The centralized file system could be Lustre. And you can have tiering on the inside between spinning disk, sleeping disk, and tape, using a piece of HSM software, in this case DMF, to manage it all. This is what I've just explained. Basically, to you and the user, your 10 exabyte of data is just one big repository to which HPC data is being put into. And you leave it to the policy of the machine to decide which type of media for it to be placed on. Yeah. But that's not the only way to do it. A new and emerging way is the Hadoop file system. This is where we are starting to see, we've sold so far, in fact, in the federal space, more than 50 of these Hadoop systems now. Worldwide, we probably have shipped 100 of these Hadoop systems, about 10,000 nodes in all. And basically, this new method of storage is a distributed way. Instead of giving the user a perception that everything is on one big disk drive, you break it up into many small drives, each with CPUs. So you have one socket to 2 drives, for example. And what happens in a Hadoop file system? A big file comes in, and it reaches this head node called the name node. And basically, that big file is then broken up into 64 megabyte pieces. Each piece is then copied 2 other times. And then all the pieces are then sprinkled across all these spinning drives. This method is useful so that if any of the servers in that picture fails, the name node knows where to retrieve the other copies to reconstruct the file for you. That's the benefit number one. Benefit number two is that if you have any computation to be applied onto that big file, you can apply it in parallel. And we are starting to see some of the users migrating to this approach. But again, this is still going to be the mainstay approach for a while, we believe, because there are still a few things that you can't do with this, given that most of the parallel computation to be done on the Hadoop file system is done through MapReduce, and it's not very HPC friendly today. And let's have a look at an example of a Hadoop file system. This is one of them. You can have rows and rows of these racks, and each of these racks have a tray. And a tray, in each of the tray, you have two of these. All right? And then you scale it up, and this becomes your one big disk drive, so to speak. It's just that when you send a file in, it gets broken up into pieces, and is sprinkled across all those servers. Yeah. So how do you then do the next thing? Once the HPC data is generated, it's massive, you do data reduction, then it gets into one of these two types of repositories. Centralized on top, distributed at the bottom. The next thing is, how do you analyze that data? Well, in the central repository, to analyze it, you can use the shared memory approach, where you suck the data back into your HPC system to do analysis. But this is shared memory non-coherent, meaning the CPU of this, in this node can read the data in its neighboring node, but after reading, you are not assured that you'll be told if there is a change. But you can read everybody's data, but you're not told if there is a change. Different from this, which is totally distributed, where it is not easy to read the neighbor's data, but you don't quite care, for example, in a MapReduce case. So these are the two approaches where you start to go to the next stage, which is after storing, you would like to analyze. And then finally, we do have another system where your analysis is kept all in a single coherent way, where you would like to move one level up from distributed to shared non-coherent to all the way shared coherent, where when you read your neighbor's data and when you have that data, if the data gets changed, you will be told about it. Yeah, and this is the example of a shared coherent system where certain analytics problem will find it very useful. And in this list, you will see who have gone into that. You can see the largest system is at Pittsburgh with 16 terabytes of shared coherent memory. And we have roughly about 10 systems so far now that are about 16 terabytes in size. The two blue ones are the new generation systems with the Sandy Bridge processor that will scale all the way to 64 terabytes. This is Professor Stephen Hawking's machine at 14 terabytes. And this one is not named yet. It's in the UK for genomics because the machine has not been installed yet. We just got the order at 20 terabytes of coherent shared memory. Let me see if I'm given permission to, cleared permission to log in into Pittsburgh right now. Let me check. Yeah, I'm logged into Pittsburgh right now. So basically, I'm logging into this machine right now, the Pittsburgh 16 terabyte machine, thanks to Jim Katstoff, who is here. Now, what does that 16 terabyte mean to you, right? Now, this is Pittsburgh Supercomputing Center. There we go, right? Now, the interesting thing about the coherent shared memory is that if I ask for how much memory, I showed this last time here before. I type map info, which is how much memory do you have in this big one node system. It will tell me I have a kilobyte, megabyte, gigabyte, terabyte, 16 terabytes of memory. So when you type the free command in Linux, you say how much memory do you have free, right? Yeah, it'll tell you I have 15 terabytes free. So far, only 1 terabyte has been used. Probably the machine just got booted, right? So imagine now you have 15 terabytes, 16 terabytes of memory in one node available, fully coherent to you, and you can load a massive piece of data in it. Yeah. How massive? Let's have a look at a very simple example where you are taking a cube that is 1,000 grid points in the x direction, 1,000 grid points in the y direction, and 1,000 grid points in the z direction, and then you're taking that cube and you're marching it 1,000 time steps. That seems like a very logical way to think about your data analysis problem. But the only problem with that is that you have 1 trillion grid points in that data set. If every point was 8 bytes, this is 8 terabytes of data. Try doing it on your laptop, right? You probably take a few weeks just to page through your disk drive, provided you have 8 terabytes of disk drive to page to, right? But on this machine at Pittsburgh, that's the reason why it's popular for especially people like genomics. You can just compile ba.c. It will compile, right? And I can just run it and gobble up for no reason the entire 8 terabytes of that 16 terabyte machine. I'll stop it right here before Pittsburgh calls me. Yeah, Jim is here, right? Thanks, Jim. I did stop it, Jim. Right. There we go. Right. So that's the reason for these machines up there. Basically, they present to the user the perception, physical perception. Actually, it's not perception; it's real. Of 16 terabytes of basically a 16 terabyte PC. And that's basically the entire picture, right? After your HPC system or your big instruments have generated the data, there are 2 ways to keep them, right? In a centralized way or in a distributed way. But currently, this is still the most popular way because it is most flexible. There are some restrictions on the map-reduce operations you can do here, but research is going on to expand its capability. And then you can also do analysis under these 2 approaches. And then if you need to take one level up in your analysis, where you would like to keep all your 1 trillion grid points, for example, in one coherent space, there is yet another machine called the UV system to do it. That essentially is the landscape of most of our customers out there. It basically touches on most of our customers out there in terms of the HPC and big instrument data. And lastly, we are also seeing a pickup in another data generator. Interestingly, in this whole list, especially the newer ones, many of them are additionally asking for accelerators to be put in there. Not just using these Intel Sandy Bridge processors, but also to put in these accelerators either from NVIDIA or from Intel, which is the mic processor. But so far, most of them have been picking up the Intel mic processor accelerator. I brought a sample it from Intel here. And basically, many of these systems, in addition to the Sandy Bridge processor and the 16 terabytes of memory, are asking for many of these cards to be plugged in also. The key thing about these cards is that this processor here uses the same cores as your Sandy Bridge system, except that instead of having only 8 cores in a Sandy Bridge Xeon processor, you can have 60 cores in here, 50 cores. Yeah? Intel is saying that you'll be more than 50 cores, and we'll see what the number will turn out to be by the time they release the product this year. So that's a neat thing. So let's have a look at its strong point. Its strong point is, in addition to the fact that you have more than 50 cores in one chip, and imagine you put 100 chips of these in that system, the strong point is that it's easy to program. Let's have a look at a sample card that we plugged into a server. So I have a server here with this card plugged in. And you can see from this, this list that there are many, many cores in this card, right, in this chip. It's showing 30 here, but by the time the product is released, it'll be more than 50 cores, right? And currently, all the cores are free. Yeah, you can see on the user side, it's all 0% used. Let's show you a toy program to show how easy it is to program. So we wrote a toy program called pi.c, and all it is just a loop to do some computation. And the other thing I did was to put an OpenMP statement so that all this will run in parallel. This is a normal C code that should normally run on a Xeon. All right? How do I run it on the more than 50 core chip? All you do is compile it with OpenMP like normal, and then pi.c. Normally, when I do this, it should run on the Xeon. But how do I get it to run here? All I do differently to get it to run here is to add in this case, MMIC. That's all. This extra switch to say that when you're compiling, compile it for this 50-core chip. Hit a return. And then now I become super user, and I log in to this card directly. I log into this card directly. Go to the directory that has this compiled program, and then I run it, the a.out. So watch this column of 0% when I hit return. You can see, yeah, 100%, yes. There we go. All the cores are activated. So the key thing why many of these customers on the list have also asked for these cards to be plugged in. You know, some are asking for 16, some 32, some 64, plugged into the system. It's so that they can get up and running quickly with using their existing Xeon processor code. Just recompile it with that MMIC that you see highlighted, right? And away at least they can go to get things going, right? Of course, they have to spend time tuning it. And not only these customers have asked for these cards, we have also got the original HPC cluster-based, InfiniBand cluster-based customers. Many of them are anticipating these cards to be embedded in the system also. So in summary, yeah, HPC systems generate massive data. We have big instruments also generating massive data. And more now, we are seeing in HPC procurements, focus being placed on the data repository. And there are two kinds. The mainstay kind on top and the new emerging kind at the bottom that are still quite restricted in its capabilities. But it's cheap, it's easy to experiment with. Many are starting to have them, the Hadoop file system. And then when you go into the analysis phase, you can then look at either using a shared memory non-coherent approach, which is the InfiniBand-based cluster, or a gigabit Ethernet distributed memory analysis. And don't forget, there is the fully coherent big PC approach to analysis. And if you need more information, please go to YouTube for these 3 different videos that will emphasize each of these specifically, right? And YouTube, you just search for Demonstrate UV or the 2018 number or Eng Lim Goh. It will give you further details. On this note, I hope the message comes across that more and more now do focus on how you deal with that data, because we do see customers, after spending tens of millions of dollars on the HPC system, generating data, and much of that data has been left untouched for a while. I think the point must be that the minute you generate the data, you must have the capability to extract insight from it. On that note, thank you. Yeah.